Good afternoon. My name is Deirdre Hollingsworth and I am one of the co-organisers of this series of workshops called Future Pandemics within the Isaac Newton Institute series of presentations as part of the Infectious Disease Pandemics programme, which is in response to the COVID-19 pandemic. I'm the first speaker this afternoon and I'm delighted to be joined by Anna Vassal, who will be giving the second presentation. Just going to adjust one thing. That should be good to go. All right. Okay. So I'm mainly going to be talking about neglected tropical diseases, which I will tell you what they are in just a minute, but I will make a few thoughts about why they are relevant for pandemics, given that very few of them have real pandemic potential. So in this talk, I'm going to be representing some research from quite a diverse group of researchers that I collaborate with. I'm very fortunate that I work across a number of diseases and with a number of fantastic collaborators. And a lot of the work that I'll be talking about was done as part of the Neglected Tropical Disease, or NTD, Modelling Consortium, which is very generously funded by the Bill and Melinda Gates Foundation. And my work is also supported by the Lee Ka-shing Foundation. And these are some photos of the Modelling Consortium. This was from our first meeting. We were trying for an indie band cover at this stage, but by this stage it became sunnier in Warwick by the time we'd finished. So the reason that neglected tropical diseases are sort of relevant to many infections is that they reflect the fact that infectious diseases really target our social geography. We know that some people have better access to healthcare, some people have better access to sanitation, some people have better access to nutrition, and this has consequences for infectious diseases. And if we think back, even back to the 1918 pandemic, there was a paper recently published showing that socioeconomic status was associated with infection in the first wave of the 1918 pandemic. And indeed, I'd seen another analysis, which I unfortunately couldn't find the reference for this talk, but people with, I think it was with insurance, health insurance in the USA, were able to, were less likely to be infected with influenza in the first wave as well in the USA. And it's also a feature of the current pandemic that particular groups are more at risk of both infection and death. And this is an opinion piece that we published, I think it was yesterday, in the BMJ's New Opinion blog site with Rebecca Bagley and Monique Paris in Leicester University. And we were trying to highlight the fact that although we know that ethnic minorities were disproportionately affected in the first wave in the UK, we really don't have a good enough understanding of why that was to prevent that happening in the second wave. And it's a real challenge, not only in terms of protecting vulnerable groups, but also in terms of the transmission dynamics. If we want to have effective control of infectious diseases, then we need to understand what drives these heterogeneities in risk, and we need to be able to prevent the spread of infection in all population groups, not just the largest population groups. So now I'm going to tell you a little bit about neglected tropical diseases. So these are infections, which are mainly infections, so it also includes snakebite now, that cause a large burden of chronic morbidity and mortality in the lowest income population groups in the world, predominantly. It's not only in those groups. They tend to, most of them have not very high rates of mortality, although some of them do. And mainly they cause a large burden of this chronic morbidity. So, for example, many of you may think that leprosy is not such a big problem in the world anymore, but it's not true. There are hundreds of thousands, well, around 100,000 cases a year are reported, and they cause this kind of chronic problems for the population. And here we have a classic example. The left picture is of river blindness, and this is a disease which is transmitted by black flies. And in populations where there was very high risk for onchocerciasis, which is the worm infection, which causes this blindness, you can see that you often saw the younger generation leading older generations with a stick because the older generations had gone blind. This disease can be managed with a very cheap, very easy, safe to use drug, and you never see these populations, thank goodness, anymore. And that's because of the huge number of interventions which have been put in place relatively cheaply. So neglected tropical diseases are marked in the Sustainable Development Goal, partly because they can be a marker for universal healthcare. If we can reduce the burden of these diseases in these populations, then we're having a real impact on trying to break the cycle of poverty. In 2012, the neglected tropical disease community was brought together by the World Health Organization and a number of other organizations, including the Bill and Melinda Gates Foundation, to say this can no longer continue. This chronic burden of morbidity due to these diseases has to end. And it was an interesting meeting because it not only included the World Health Organization and donors such as the World Bank and DFID in the UK and USAID and government representations from endemic countries, but it also included 13 pharmaceutical companies who all made a large donation of drugs and a commitment of drugs, and in some cases diagnostics, over the next years until 2020 to really try and reduce the burden of this morbidity and mortality for 10 of these diseases. This was a huge effort, and there's been a huge investment over the years, and it has made really great progress, but it continues to have some challenges, which I'm going to talk about in a minute. Following this declaration, we were invited to put together a modelling consortium to address some of the questions which remained about the epidemiology of these diseases. In particular, how can we reach the 2020 targets as they were in terms of reducing the burden of morbidity? And I'm going to talk about a couple of aspects of these interventions, but just to note, as I showed in my photograph earlier on, the work that I'm presented is really a collaboration between a number of different institutions, and we're very grateful for the opportunity to work with them. Broadly, and this is really a broad stroke, neglected tropical diseases can be divided into two groups, although the language around this is now changing. One is mass drug administration. This is where on a regular basis, for example, yearly or 6 monthly, a drug with a very good safety profile is given to a large group of the population in a particular district or a particular village, and that reduces the level of infection in the population and gradually pushes down the new infections, the rate of new infections in that population. And some of the examples of diseases which are treated in this way are trachoma, which is caused by a bacterial infection and can lead to blindness, lymphatic filariasis, which I'll talk more about in a minute, onchocerciasis, which is the one I spoke about just a minute ago, which is river blindness, soil transmitted helminthiasis and schistosomiasis, which are both intestinal worms, well, they're worm infections really, which are associated with poor sanitation. So they're either transmitted fecally or in the urine. So of course, classically associated with people who have poor access to water, sanitation and hygiene. Then the other group of diseases which we think about are intensified disease management diseases, such as leprosy, which I also already mentioned, or sleeping sickness, also known as human African trypanosomiasis, Chagas disease in South America, and visceral leishmaniasis. And these are diseases where we only see the tip of the iceberg, hence the picture on the right. We only see either cases that turn up for treatment, or we possibly have screening programs. On the left is a picture of a screening program for sleeping sickness where you have to go out and find out who is infected. And this tip of the iceberg problem is really very large for these diseases. For instance, in leprosy, you don't see symptoms until maybe several years later. And the same with Chagas disease, you may see the symptoms of the infection many years after it has already caused the damage to someone's heart, for example. And this, of course, has some relationship with coronavirus. When we think about when it first emerged, we were really only seeing the tip of the iceberg. We were seeing the severe cases and deaths in hospital, but we weren't really sure how much other infection there was out in the population. And this is really an ongoing challenge. So I'm going to focus quite a lot on mass drug administration. So as I mentioned, in this graphic on the right, you can see we have some level of infection in the population. You come along and try and get high coverage of the number of people to be treated, and you treat them with a drug with a good safety profile, and you hope that you, sorry, I'll go forward again, that you have enough coverage of the population to prevent, you have enough coverage of the population to reduce the level of infection such that when there's new infections happening, before you come and treat again, this level doesn't get all the way back to the beginning. So if you only treated a small proportion of the population, it might bounce back before you come back a year later. But overall, you want to get a good coverage of the population and then come back again and again and again and try and reduce the level of infection in the population. Now, if you're lucky, you may get it so low after a few rounds that the infection actually dies away. And there's a whole load of really interesting mathematical theory about the breakpoint for worm infections, or just stochastic extinction for bacterial infections. But you can see that for very small differences in the coverage, you may not get to a low enough level, and the infection may bounce back if you stop doing your mass drug administration. One of the curiosities, I guess, about mass drug administration is as time goes on, you're still treating the same number of people, but the number of people that you are treating who are infected starts to decline. And so you get sometimes some resistance to continuing treating beyond this point. But it's very hard to do a study where you can actually evaluate what proportion of the population are infected at such low levels. And so there's always then a debate about whether you should carry on the mass drug administration even further. One suggestion that is often made is that you lengthen the interval between mass drug administrations when you get down to this low level, but actually you just end up at a new equilibrium if you do that, and you may even see slow increases. But in terms of health systems, and I'm looking forward to Anna's talk later, it's a health economic decision which of these strategies are better in terms of the impact of health in the population. So in terms of modelling questions, the sorts of questions we're asked are: who should be treated, how often, and for how many years? Importantly, what is the impact of a systematic non-access? So even in these low-income populations, there are parts of the population that do not access healthcare, or perhaps they're the population who are not in when the mass drug administrators come around. How can we effectively combine interventions? How can we measure transmission in order to stop? So at this level, you have to sample a lot of people to know whether you're at a very low level. And how do you measure it after you stop treating? But the challenges for us as modelers are two other things, which are: how do we validate the models given the limited amount of information that we have? And what is the role of spatial heterogeneity? And I've just shown some maps of lymphatic filariasis in sub-Saharan Africa here. And that's just one example of the challenges of spatial heterogeneity in these populations. One thing that's really important to remember in any health intervention is that there's always a heterogeneity in response, even if you think you're applying the same treatment to different populations. So this is an example of trachoma, which is a bacterial infection I mentioned earlier, which can cause blindness. In a number of villages, they applied the same intervention. They think they treated roughly the same number of people. They counted the number of people they were treating, the same proportion of people. And so in the black line, you can see the average behavior, which is that the level of infection gradually goes down, and then when they stop treating, it gradually responds. But the light grey lines are all the different villages, and you can see you get a very different response in the different villages, despite the fact that you think you're applying the same intervention. And in particular, in the rebound here, we see some very rapid rebound in some villages and slow rebound in others. And this is a real challenge for the programme. How do we identify those villages in a cost-effective way? And do we understand epidemiologically why this one has rebounded so much faster than this, when presumably it was going along quite nicely through these rounds? So one of our questions is, what should we be measuring to understand this heterogeneity response? And how will we know whether or not we've eliminated, because there are also some villages here which look like they might have eliminated, and then we see the rebound of infection. So an important underlying factor in both those questions are heterogeneities in transmission. For the worm infections that we study, we have a very skewed distribution of worms. So some people have lots of worms and some people have very few worms. And is this a surrogate for biting risk? So this is a disease, lymphatic filariasis, that is spread through biting mosquitoes. And one of the questions always is, to what extent do these people have lots of worms because they're getting bitten much more, or because they are just sort of genetically predisposed to have many worms, to be more susceptible, or is it that it's just chance that this person has more worms? And this is really important because it has important consequences for the dynamics of the infection. So this is an illustration. These different coloured lines are the equilibrium prevalence of this disease for different levels of biting between people. So this yellow line is fairly close to mosquitoes randomly bite everybody. And so if mosquitoes randomly bite everybody, you need to have quite a lot of mosquitoes. So this axis here is the vector host ratio. So this is how many vectors per human. You have to have quite a lot of mosquitoes in order to get a good level of transmission. So that's because if they're randomly biting everybody, if it bites me today and then doesn't bite me again, I don't get bitten again for a while, then I can't transmit on an infection that I've acquired. Okay, so I need a fair number of mosquitoes, but once I have enough mosquitoes, I can get really very high prevalences in this setting. So now let's consider another extreme, and this is the blue line, where let's say one group of the population is being bitten by the mosquitoes a lot, and the other half of the population, let's say half of the population, is really not getting bitten that much. Well then, what happens is that we can't really get to very high prevalences, even if we have lots of mosquitoes, because the mosquitoes are all biting the same people and they rarely bite the rest of the population. So I can't get to a very high prevalence, but I don't need that many vectors to have an epidemic, because effectively I have a sub-epidemic in this population who are predisposed to getting bitten. And so what this means is that somewhere that seems to have low endemic prevalence, if you then introduce an intervention where you're reducing the number of vectors around, so if you have bed nets or you're spraying to kill the mosquitoes, you would think that place would be fairly easy to control the epidemic, but actually it's very resistant. It's very robust. So even if you get the number of mosquitoes down a lot, you can still sustain transmission in this population. So this is just one example of why heterogeneity is so important to understand the dynamics of an infection that we're looking to control. So one of our questions about this was, is measuring this worm distribution sufficient to understand where we are on these curves, or do we need to know more? So we were fortunate to collaborate with a lady called Lisa Reimer at the Liverpool School of Tropical Medicine, and we did some analysis of hers where she had different data sets from different villages. And this is kind of the modelling construct that we used for that analysis, which is that there is spatial heterogeneity. So some villages have more of this disease and some have less, for example. And that may be driven by the fact that one is higher up a mountain, so it's less suitable for the mosquitoes, or one is closer to a mosquito breeding site. And then within a village, there's individual heterogeneity. So even if you're in a village with a high level of transmission, you may not get that many mosquito bites. And similarly, if you're in a village which has a low level of transmission, you may be the person who gets lots of bites. And then each of those things has a consequence for the distribution of worms that we would expect to see in the population. So we were fortunate through working with Lisa to have multiple measures in a single site. So we had vector biting, so they had measured the extent to which there was variability in getting bitten using human landing catches. They had measured the number of worms in people's blood, and they'd also looked at, which was the data I showed you before, this microfilariae, this is the number of worms in people's blood. But they also had measures of antigenemia, which is a measure of the adult worm in the number of adult worms that people have in their bodies. And we had it in multiple locations. So here's some representations of the data. This are the number of nightly bites. which is very highly variable across these sites. And then also the average number of microfilaria or baby worms in the blood. And you can see there's again a huge variability. And of course, what's interesting is these two things are not overlapped, don't overlay very precisely. You can really see there's a difference between these areas, these measures, sorry. And this is also shown here. So this is nightly bites. This is the variability shown by the box plots in the different villages before and after the introduction of bed nets. So before the introduction of bed nets, they're all quite different, and they do respond reasonably differently to the bed nets. Although there is, there are some similarities. They all reduce obviously the biting, but there's still differences between the villages. But the night bite isn't enough to tell you which places will have what response to the bed nets. And here we have the same villages with the number of microfilaria in the blood, and you can see that this pattern is very different from the pattern on the left. So our nightly bite is not predicting which villages have the highest levels of this infection in the blood. And even if we try and use a spatial model to account for some of that variability, we still get very different results for the amount of transmissible worms and the bite rate. We're really getting very different patterns. So this is a really big challenge for us. We don't have very good measures of the heterogeneity which is affecting transmission for this disease. And that's okay in a sense that we can manage that to an extent, in that we mustn't overinterpret the data that we do have, but it is a challenge in terms of designing elimination programs in particular, which is part of the aim of the lymphatic filariasis program. So on top of all that biological heterogeneity, we also have human heterogeneity in how we respond to a program. And this was a study by Louise Dyson at Warwick. And she was looking at how modelers represent heterogeneities and how people respond to a treatment program. So here on the left, we have a random treatment program. So in round 1, randomly the red people are treated, and in round 2, randomly the red people are treated, but there's some overlap between the people who are treated here and here, but it's not complete. We could have, as I was mentioning earlier, there can be systematic lack of access to a health intervention for many different reasons. It can be to do with gender, it can be to do with where you live, it can be to do with your socioeconomic status. But here in this representation, the people who are closer to the centre are more likely to be treated, and the people who are further away are less likely to be treated. And then at the extreme here, we have that these people always get treated and the others never get treated. And then we have sort of a modelling approximation to it in the middle. So we know that this is a real effect, but again, we have very little information for mass drug administration on which of these patterns are more prevalent in which populations. And we know from modelling that it has a lot of consequences for how successful a mass drug administration program is likely to be. And one of the compounding problems is that often we tend to be able to measure infection in the people who we treat. So the people who we treat are most likely to be also involved in our surveillance programs. And then that is a very big challenge for understanding the dynamics of any infection. So how important are heterogeneities and when are they important? In the study that I showed you a minute ago, we saw that here we had the nightly biting rate here, and we have this measure of heterogeneity here. And we saw for all of the sites that introducing bed nets moved you from a high level of biting to a lower level of biting, but to a different extent for the different sites. And that it also changes, which I didn't illustrate earlier, the extent of heterogeneity. So you actually end up having more heterogeneity for lower values of K once you introduce the bed nets. But nonetheless, the number of rounds of treatment that would be required to eliminate this disease would be reduced, of course, by bed nets. So again, this is a challenge. Once you introduce an intervention and people respond differently to it, that then impacts how much more interventions are needed at different sites. And we're very unlikely to be data rich in a new pandemic. So we need to understand a bit more about these behavioural and socioeconomic interventions. For lymphatic filariasis, I mentioned earlier that there's lots of interesting maths around the breakpoint. So I'm going to just touch on it a little bit here. So there's two main processes at play when a worm infection, human worm infections that I mentioned earlier, are eliminated. The first is this theoretical breakpoint. So there's sexual reproduction in the human host, and that means I need to have an adult male and an adult female worm in the same host in order for them to be able to reproduce successfully. And as we showed that skewed distribution of worms across people, as the average number of worms falls, it becomes more and more unlikely that a male and a female worm be in the same host. And that means that once you get down to a low enough average number of worms in the population, you're likely the infection will just die away by chance, because will just die away, not by chance, will die away because of this feature that you have to have a male and female worm in the same host. Now, on top of that process, we also have stochastic extinction, the element of chance. So we know that as infection numbers become low, the number of people infected becomes really important, and by chance somebody may transmit or may not transmit. We know that both of these effects are dependent on population size, biting patterns, and the bite rate. And of course importation, which I'm not going to dwell on, but if you have of course imported cases, they can introduce new chains of transmission. So there's a lot of questions about, for lymphatic filariasis, the disease I've been talking about most. There's a lot of questions around the stopping points. At the moment, mass drug administration is halted when the proportion of people infected falls below about 1%. And there's a protocol by which it's measured, but for the purposes of this talk, let's think about it as 1%. And the question is that sufficiently low that the new infections will die away, or the existing infections will die away and no new infections will happen? So one of the features of our consortium is that we have multiple models per disease. And here I've presented some results of simulations for a range of parameters, a range of settings, where you bring prevalence below 1% and then you see what happens. For the grey simulation, so there's many simulations on this plot, the epidemic eventually dies away or stays below 1%, doesn't necessarily die away. And for the red one, it rebounds. And because we've got a deterministic model here, a stochastic model here, and a different stochastic model here, we get quite a range of behaviours. So the behaviour of this deterministic model is determined by the breakpoint, but here we have stochastic events happening. So one of the things that when we presented this to policymakers, they were most interested in is I had some researchers from Sri Lanka and some public health experts from Sri Lanka, and they had no one had ever been able to explain to them that why in Sri Lanka prevalence just seems to drift around 1% but doesn't die away. And it seems that in some settings for this disease, 1% is a threshold where it just kind of sits here and it takes a very long time to either rebound or fade away. And this is true of many diseases for which there is a slow epidemic growth rate. When you perturb the system and go to a new state, it can sit at this state for quite a long time. And the determinants of whether something bounces back or not is definitely to do with the biological parameters, but there's an awful lot of chance events involved as well. So population size becomes very important. And again, you know, this heterogeneity, this population structure, our social geography is really important in determining how big our local population with whom we can transmit diseases is. And again, we don't have a fantastic understanding of that in general, but also for these particular diseases. The good news is, of course, about this disease is that it actually takes many years to rebound, and the current protocol tests 3 years after stopping and another 3 years later before declaring that elimination as a public health problem has been reached. So I'm going to take a little bit of a sidestep at the moment and also look at, in terms of pandemics, their impact on other diseases. So I'm going to look at the impact of coronavirus 19 on neglected tropical diseases, and this is a report that we published recently in Gates Open Research. So when we think about future pandemics, we need to think about not only about the infections themselves, but their impact on other diseases. And classically, there are estimates for Ebola that the number of deaths from other diseases was higher than the number of diseases due to Ebola itself. So, of course, in 2020, neglected tropical disease programs were affected by COVID-19. The World Health Organization, WHO, responded very quickly and advised that non-essential mass drug administrations were halted, but that, obviously treatment of ill individuals should continue, and some other processes. And then more recently, they've published a guidance on how to do a risk evaluation balancing NTDs against COVID transmission, which is very challenging, I believe, for countries to consider, but some NTD programs are going forward. So we were asked what was the impact of disruptions to NTD's activities, what is the impact of that on NTD transmission, and how long can NTD programs be postponed before progress towards the new 2030 goals, which were set last year, or I guess are currently being set this year, how long before they will be adversely affected. So we did a number of simulations. Here we think about, let's say you did your mass drug administration in March every year, you did your 2019, you missed your 2020 round, and you're doing your March 2021 round. What is the impact of the fact that you've missed this round? So most of the results will be this scenario, but obviously every district will have a different scenario for how long the delay will be between this round and the new round. And also there may be different mitigation strategies which can be delivered in the years that follow. So for PC diseases, which is another way of describing the mass drug administration diseases, the preventive chemotherapy, we have a scenario where you were going to treat like this every year. This is an example of schistosomiasis. And this was when you were going to reach elimination as a public health problem, which are these thresholds in terms of prevalence of high intensity infection. But instead you missed a round, and so you're now on the black line, and it'll take you an extra 2 years, even though you've only missed 1 year, it'll take you an extra 2 years to reach the target. And on top of that, in the yellow areas, you have the additional burden of disease. And the longer the delays, obviously, the greater the resurgence in infection. And in high transmission settings, where this bounce back rate is faster, obviously, the bigger the impact. And one of the mitigation strategies which was considered is that when the next round comes in 2021, that it has high coverage and includes adults, is community-wide. And then the impact of the COVID-related interruption is reduced both in terms of morbidity and delay. And indeed, for some strategies, you may even see that not only do you, if you maintain this strategy, that you sometimes even reach elimination as a public health problem earlier. So I mentioned earlier on, but I haven't really come back to it until this point, that case-finding diseases are a feature of neglected tropical diseases. So I mentioned leprosy and visceral leishmaniasis, where you tend to only see the symptomatic cases, and we know they're only the tip of the iceberg. So one of our challenges for these diseases is generally our understanding of the natural history is really very poor. And so we don't really understand how fast epidemics grow. This is particularly true because our diagnosis of cases affects transmission and therefore affects what we see in order for surveillance. Our understanding of surveillance is affected by our case finding. So I'll give you an example here. So this is an example of visceral leishmaniasis. And here in the black line, we have a simulation of the true level of visceral leishmaniasis in the population, new infections. And then this is what we observe. So we have a sort of an okay diagnostic system. And so we find some cases. Now we start to scale up and improve our surveillance and diagnosis of cases. So then we start to find more and more cases, but the actual underlying level of infection is falling because we're finding all these cases, and eventually we're getting good enough at it that we're actually, both things are falling. So true incidence is falling and the number of cases that are falling. This is one of the challenges for case finding diseases, is that once you start to look, you will find a big backlog. But eventually, if you have a good case finding program, you start to see reductions in the number of cases. So fine, things are going well, the number of cases is falling, the number of deaths is falling, but now we have an interruption to the program. So we start to find fewer cases. So it looks like incidence is falling, but that's because our program is no longer finding them as effectively, and our underlying level of incidence starts to grow and we can't see that happening. And then eventually, even though our detection is poor, we do start to see a climb in these cases. So for these diseases, the interruption to the programme due to COVID-19 is really very challenging because it affects not only our diagnosis and treatment of cases, but our observation of the process. So obviously, delays to the goal will depend on the phase of the programme and the transmission setting, but we really need to try and maintain as much as possible our detection and treatment of cases. And that is really very challenging. Mitigation strategies, potentially vector control for some of these diseases, but it really will require that the programme comes back strong when it comes back in order to prevent a large resurgence. So I'm coming to the end. I'll just summarise some of the results from this work on COVID-19. As I say, you can find it on Gates Open Research. So delays due to COVID-19 will lead to increases in infection and morbidity, and therefore increased time and resources to reach the 2030 targets. But this will depend on which particular neglected tropical disease you're looking at. And not only that, but the local transmission dynamics, that spatial heterogeneity I talked about. Also the delay and, and some chance events mean that some villages will have a bigger impact than others, or some districts will have a bigger impact than others. For the diseases that we work on, the impact is greatest for high transmission areas for schistosomiasis, trachoma, and visceral leishmaniasis in the Indian subcontinent. And this is particularly true in high transmission areas. So I thought at the end I should bring us back to some thoughts about pandemics, given our work on neglected tropical diseases. Well, pandemics, we have this problem of we want that our case finding is affecting transmission. So we have this problem that we probably have very poor understanding of the dynamics in the early stages, because when we find more cases, it's because we often talk about an epidemic of diagnosis at the start of a pandemic. We suddenly find a lot of cases once we start to look. And that means we have a lot of uncertainties in key parameters. And also our contact tracing can have very uncertain efficacy. And of course, human behaviour underlies all our understanding of disease transmission in humans, and we really have a lot to learn, I think, in that area. For COVID-19 and indeed for any emerging pandemic, there's always discussion around elimination, and it's really challenging to achieve. And that's because it's very difficult to measure often. Measuring zero is a huge task. And it can be very difficult to maintain if you get there, and that's indeed what we've found for COVID-19. But also our transmission models are least well validated at very low levels. So we really, we tend to have data once a pandemic gets going, or for any infectious disease really, you tend to do epidemiological studies in places where the level of infection is quite high, so that you can see an impact of an intervention, and because you have limited budget to measure huge proportions of the population. In addition to that, there are the unknown unknowns. I've shown here a picture of guinea worm in dogs. For those of you who don't know this story, guinea worm is close to global eradication after an enormous and hugely successful effort. But in the last few years, of course, they discovered that there was part of the life cycle was in dogs, and this may or may not be maintaining transmission in the humans. And so that has been a real challenge to such a hugely successful program. Some would say that could have been predicted, but I would say, it didn't prove to be a problem anywhere except one particular place, and now, it's taking a few years to overcome it, to understand it. And that's the challenge of infectious disease epidemiology. There are just so many unknowns, and if you're going to go for elimination, that's when those unknowns become particularly important. I've put immunity question mark here, I think, just to flag that, of course, for COVID-19, we're still uncertain about the extent and duration of immunity, and that will impact any public health decisions over the next few months. I want to come back to my theme, from working on neglected tropical diseases and also working a little bit on coronavirus this year and working on infectious diseases in general, infectious diseases do travel along the details of our social geography. And not unlike other things, inequity is a feature of many public health challenges. It's not just for infectious diseases, but infectious diseases are different to some other diseases in that an infectious disease which spreads in a population that I'm connected to affects my risk. And so there should be motivation for us to improve health services to all populations, not just the populations which we are part of. And, you know, this has been shown time and time again, even in terms of sort of pandemic response, that there was a global donation to provide a response to whichever country happened to be subject to the emergence of a new pandemic, influenza. So it's well recognised, but it is worth restating. And just to talk about modelling within that context, I mean, modelling is a tool to be used as part of the effort of understanding transmission and motivating responses which are appropriately tailored to different populations. But modelling always relies on good communication by both the modellers and the people asking the modellers questions in terms of what's the question and what is the required output. And it does require on good data. And I know modellers are always banging on about data, but I think, you know, this pandemic has shown again that modelling can be used when there's limited data, but then it has to be a really careful communication challenge. And then just really a call to have that virtuous circle of understanding heterogeneities, then having interventions to address those heterogeneities, and really keeping that as an active conversation throughout a pandemic. And I think I'm going to finish there. It's just about 1:45, and just finish again with an acknowledgement slide. This is just some of the people that I've been fortunate to work with. And I think I'll see if we have any questions. Thank you very much. So I don't know if we have any right now. I know Anna is ready if by any chance.
No, there was a question.
From Andy, please go ahead.
No, there was a question from Valerie that she typed into the thing. It says, higher biting rates or some bites delivering a higher parasite load.
Oh, good. So yes, an ongoing challenge again is the relationship between biting rates and parasite load. Yeah. I think you were probably talking about the plots of biting rates and prevalence maybe. Yeah, but it's about how many potential exposures you have, whether that's more parasites or more vectors. But yes, for many diseases, there is quite some heterogeneity in the number of infectious parasites you get per bite. So that again is another layer of heterogeneity which I could have discussed.
I mean, one thing that's consistently struck me about both in the talk, which was super, but over everything we've been banging our heads against since the first Newton meeting that I dimly go back to, it is how does heterogeneity change as we reduce vector abundance, as we reduce worm abundance? My intuition is that it would become more Poisson and more random, but then everything you've suggested and other people I've talked to suggest for some reason it becomes more aggregated. And does it suddenly flip at some later stage, or how on earth would we get data to try and quantify that?
Great points, Andy, as always. Yeah, so there is data from the Tumakia study, which was a large deworming study, which looked at trying to eliminate, getting close to elimination for hookworm in particular. And they did measure it at multiple points, and they did find, exactly as you're saying, that there's more heterogeneity as you get down to low levels. And that is partly because I think of heterogeneities in behaviour and heterogeneities in exposure. As you say, at some point, you must get into that group of population who are sustaining transmission. So there must be some kind of flip once you get really low, but unsurprisingly, the worms are cleverer than us and are actually well designed to maintain transmission and not be eliminated.
Just while I'm waiting for other questions to come through, and I'm happy to have people type them in onto the chat or to raise their hand, and I can point people towards those. All sorts of interesting insights there about the effect that COVID has had on controlling the NTDs. But do you think there are any either positive or negative interactions between the NTDs and COVID? Going back when we had the talks last week, there are these huge differences. I mean, COVID doesn't seem to have been as unpleasant in Africa as it's been in South America. Is this because of higher levels of NTDs creating background levels of inflammation that might be reducing the impact of COVID, or is there any evidence for things like that?
Oh, very good question. So early in that debate, there was, of course, the question that there's no health infrastructure in some of these populations, so how would we even know if coronavirus was there in some of the more remote populations? But equally, maybe these remote populations, which are, you know, talking about Africa as one thing is always really difficult because, you know, there's such variation in the levels of wealth, the levels of urbanicity. Like, so you would think in rural areas in many sub-Saharan African countries, actually connectivity is pretty weak. And but there's probably quite good awareness in the terms of, you know, through mobile phone kind of news sharing. So it may be that they were actually protected. And to be honest, I haven't seen conclusive evidence either way on that debate. So, you know, I think now we're seeing some growing epidemics in some sub-Saharan African countries, and also we're seeing better testing, etc. So we're getting better information as we go along. And, you know, I hope that as a result, they'll be better prepared maybe than some European countries.
Yeah, I mean, partly we looking at Chagas have been wrestling with the opposite side of that coin, in that there are so many people infected with Chagas that may be naturally weaker to COVID. So when they get COVID, it's an interaction between Chagas and COVID that's killing them. But nobody ever checks to see if people have Chagas. No. So again, it emphasizes how much more we need to know about it.
Exactly. And again, a massive health inequity, right? So
yeah,
it's very correlated with income.
Yeah, totally. A slightly sort of different set of questions. I mean, I personally have hugely enjoyed the NTD modeling consortium, which you've done a brilliant job sort of managing. It's interesting to compare that with some of the other consortiums, like the malaria one, where they're all working on the same thing and all at each other's throats. Whereas ours has been a much more interactive and positive, symbiotic, because it's like, oh, that's a useful thing you're doing with that disease. We could try that out with ours. So there's been much more symbiosis. Given that you've got this mass of people moving in to work on COVID modeling, what sort of advice could you give to keep all those interactions positive, which largely they have been? But what sort of insights did you get from working on the NTD?
That's a good question. So I think the good thing about people working on NTDs is I think they're not working on NTDs for the glory, right? They're in it because they care about the underlying question. And I think that is true of most people who are working on coronavirus now. Maybe not all, but a lot, you know, they're really bothered by trying to help. And while you have that, while there will always be a healthy competition, and they do want to beat each other. I mean, academia is based on some basic kind of game theory that we're all out to compete with each other. Whether you think that's a positive or a negative thing, that is the ecosystem in which we live. And so they do still compete fiercely, but fundamentally they have to work together, you know, on government advisory panels. You know, it's no help to anybody if the modelers are at each other's throats. So yeah, it's motivation. They'll all hate each other again at the end of it. So. Yeah, I mean, I don't know whether there should be collective responsibility or not. I don't know whether that would help us or not. So yeah.
No, that's an interesting thought. I mean, I do get it's like healthy competition, but yeah, it's some magical point along that spectrum.
Yes, exactly.
Collaboration without too much culling.
Yeah, I've only seen positive collaboration in the people that I've worked with on it, you know, well, and certainly in the Isaac Newton program, it's been really great. I have to say that stimulated a lot of cross collaborations, which wouldn't have happened otherwise. So, you know, because we're all so busy trying to help our national governments or contribute to our national debate, the Isaac Newton Institute has provided that forum where we can talk internationally, and I think that's been really good.
Yeah, no, it's consistently done that, and it has been fantastic for that.
Yeah.
One additional sort of worry is, I mean, the NTDs have always been classically underfunded until the sort of Gates initiative. Are there any concerns that funding for the NTDs will be reduced as it all moves towards sort of COVID?
Well, that's one of the messages of our modelling, is that you can leave it for a while, but you can't leave it too long. And when you come back, you're going to have to come back strong. You can't come back with a weak program. That's basically no point coming back with a weak program. When you come back, you're going to have to come back with a strong NTD program. And that's a message that we're trying to, just doing mass drug administrations, you've got to have high coverage, you've got to increase your case detection. And so, there's a lot to be done still with the neglected tropical diseases, and they can be left for a bit, but they cannot be sidelined. And that's why, but I think this is why the debate around universal health coverage is really important. And the NTDs do need to be integrated into health systems eventually. And what's really interesting is the response of the neglected tropical disease community. They're talking about innovation. They're saying, okay, fine, we're stuck. We realize we're not going to be at the top of the agenda for the next 6-12 months. So let's take this time to think about it. Let's think about what we can do when we come back. Let's rethink integration across diseases. Let's rethink integration with other diseases. It's been a really positive response, and WHO has been at the center of that, and I'm really impressed by the team there, how they've responded.
Yeah, I mean, I think the NTDs give us our sharpest perspective on how important social geography is, and you superbly pointed out that that's very much the case with COVID. But I wonder, are there any economists trying to model how this affects the development of different healthcare systems in different countries? And particularly, is there enough information to see how much the differences in death rates due to COVID, as well as I think we're increasingly going to see morbidity patterns due to COVID, differ because of the way that different healthcare systems have functioned or malfunctioned in the face of this different challenge? And just what insights will we get from this, looking at NTDs?
Yeah, absolutely. Another really good question, one which I'm not qualified to answer, and I won't put Anna on the spot just before she's about to give a talk. But absolutely, we need to, pandemics of any infectious disease highlight how much we are all connected, and how the weakest link in the chain does affect all of us. And it's an opportunity, it's a story, a narrative that we need to tell, and models help tell that narrative. But I think we could do more to highlight how, even if we're poorly connected, if we have any connection, then we're all at risk.
Yeah, it would be interesting to do some sort of models of something that's like the inverse of herd immunity, which I call I guess you could call it wealth susceptibility. Is how many more wealthy people get sick because people living in challenging circumstances are increasing rates of infection to those. And it's a sort of the obverse calculation, but it shouldn't be impossible to do a straightforward version of that and then be heavily criticized for not putting in all the details, but it would be insightful as well as inciting.
Exactly. No, I think so. And I think as modelers, we all know that that's true, but maybe, as you say, you already come up with some interesting language. So maybe that's how we should do it. We can put it as a challenge to this community.
Right. Good.